Fine, let's start. Number 10. The dark night sky. Go outside tonight, look up, and notice something so obvious you've never once questioned it. The sky is dark. Between the stars, there's nothing but black. And that, it turns out, is one of the strangest facts in all of physics. Here's why. Imagine the universe is infinite. Imagine it goes on forever in every direction, and it's been here forever, and it's filled more or less evenly with stars. Now pick any direction in the sky and draw a straight line out from your eye. If there are infinite stars in an infinite universe, that line has to eventually land on the surface of a star. Maybe it's close. Maybe it's unimaginably far. But sooner or later, every single line of sight ends on something burning. And if every line of sight ends on a star, then the entire sky, every patch of it, in every direction, should be as bright as the surface of the sun. The whole sky. Not just dotted with points of light, but a solid, blinding wall of fire from horizon to horizon. Day and night. No difference. There would be no night. But there is a night. The sky is black. So one of those assumptions has to be wrong. This puzzle is old. It's named after Heinrich Olbers, who wrote about it in 1823, though people had been scratching their heads over it since Kepler. And for a long time, nobody had a good answer. People tried to wave it away with dust clouds blocking the distant light, but that doesn't work. The dust would just heat up and glow too. The real answer didn't arrive until the 20th century, and it's beautiful. The sky is dark because the universe is not infinitely old. It had a beginning, somewhere around 13.8 billion years ago. And because light travels at a fixed speed, we can only see the stars whose light has had time to reach us. Beyond a certain distance, we're literally looking at a universe so young that stars hadn't switched on yet. The light from farther out simply hasn't arrived, and on top of that, the universe is expanding, stretching the light from the most distant objects until it slides out of the visible range entirely. So the darkness isn't empty. The darkness is a clock. It's telling you the universe is a finite age and that it's been growing this whole time. Sit with that for a second. The single most ordinary thing you will ever observe, that it gets dark when the sun goes down, is quietly carrying the answer to one of the biggest questions there is. When did everything begin? The night sky has been whispering it to every human who ever lived. We just didn't know how to listen. And for one quiet moment, look up and realize the blackness between the stars isn't nothing. It's the edge of time, looking back at you. Number 9. The Titius-Bode Law. In 1766, a German astronomer named Johann Titius noticed something he probably shouldn't have. He was playing with the distances between the planets, and he found that a stupidly simple little formula seemed to predict where each one sat. You start with the numbers 0, 3, 6, 12, 24, doubling as you go. You add 4 to each. You divide by 10. And what you get, almost eerily, is the distance of each planet from the sun. Another astronomer, Johann Bode, loved this so much he started shouting about it everywhere, which is why today it's usually called Bode's Law, even though Titius found it first. Such is science. Now, a cute numerical pattern is one thing. Lots of numbers line up by accident if you squint. What makes this one unsettling is what happened next. The formula had a gap. It predicted that something should be orbiting at about 2.8 times the Earth-Sun distance in the space between Mars and Jupiter. But there was nothing there. Just empty space. The pattern said, there should be a planet here. And the sky said, no, there shouldn't. Then, in 1781, William Herschel discovered Uranus. And Uranus landed almost exactly where the formula predicted the next planet out should be. A world nobody even knew existed, sitting right on the line. Suddenly the law looked less like a coincidence and more like a key. So astronomers went hunting for that missing object in the gap. And on the first night of the 19th century, January 1st, 1801, an Italian astronomer named Giuseppe Piazzi found it. He wasn't even looking for it. He was making a star catalog, and he stumbled onto a little point of light at 2.77 times the Earth-Sun distance, right in the gap. We now call it Ceres, the largest object in the asteroid belt. 2 predictions, 2 hits, a formula with no known reason to work, calling planets out of the dark before anyone had seen them. And here's the thing, nobody can tell you why it works. There's no law of physics that says planets must space themselves out by doubling numbers. The best anyone can say is that gravity and orbital resonances tend to push planets into roughly geometric spacing, and this little formula happens to fit our particular solar system pretty well. But then it falls apart. Because when you get to Neptune, the formula predicts it should orbit at about 38.8 times the Earth-Sun distance. Neptune actually sits at about 30.1. That's off by nearly 30%. Not a rounding error. A failure. So what do we have? A rule too accurate to be nonsense. It found 2 real worlds, but too broken to be a law. It lives in this maddening middle ground, where it clearly knows something, and clearly doesn't know everything, and science still can't tell you which side of the line it really belongs on. It's like the universe handed us a pattern, let us think we'd crack the code, and then quietly change the rules at the edge of the solar system. And nobody knows if we were ever supposed to find it at all. Number 8. The sun's missing spin. Picture how the solar system was born. A giant cloud of gas and dust, light years across, slowly collapsing under its own gravity. And as it collapses, it spins, faster and faster, the way a figure skater speeds up when she pulls her arms in. Almost all of that material falls into the center and becomes the sun. So the sun should be left holding almost all of the spin too. It should be whirling like a top. It isn't. And this is one of those facts that, once you really look at it, refuses to sit quietly. The sun contains more than 99.8% of all the mass in the solar system. Everything else, all 8 planets, every moon, every asteroid, every comet, every grain of dust, all of it adds up to less than 0.2%. The sun is, for all practical purposes, the entire solar system. The planets are crumbs. So here's the question. How much of the spinning, the angular momentum, the rotational oomph of the whole system, does the sun carry? If it's got 99.8% of the mass, you'd expect it to have almost all the spin. It has almost none. Depending on how you count, the sun holds somewhere around 2% of the solar system's angular momentum, maybe less. The other 98%, it's out in the planets. Just Jupiter and Saturn alone. 2 balls of gas that together are a rounding error next to the sun, carry more than 90% of the spinning of the entire solar system. Let that sink in. The giant at the center barely turns. The specks orbiting it hold all the motion. It's like watching a spinning carousel, where the massive central pillar sits almost still, while the little painted horses on the outside carry all the momentum. It's backwards. An astrophysicist named Leon Mestel put his finger on this back in 1965, and it has a name now, the angular momentum problem. When you run the models of how a star is born, the newborn sun comes out spinning so fast it would practically tear itself apart. Real young stars, including the young sun, spin far, far slower than the math says they should. Something stole the spin. The leading suspect is magnetism. The idea is that the young sun had a powerful magnetic field, and that field reached out and grabbed the hot, charged gas streaming away from it, the solar wind, and flung it outward, and as that gas flew away, it acted like a brake, carrying angular momentum off into space and slowing the sun down over millions of years. A star, putting on the brakes by throwing pieces of itself away. It's a good story. It's probably even mostly right. But here's where it gets uncomfortable. When you actually try to balance the books to account for exactly how the sun shed almost all of its spin and dumped it into the planets, the numbers don't fully close. Researchers are still arguing about the details, still trying to explain how the center of the solar system ended up as the one part of it that barely moves. So the next time someone tells you the solar system is a solved, tidy place, remember this. The thing at the center of it, the star that is basically everything, is spinning wrong, and we're still not completely sure why. Number 7. The sun's quiet orbit. You know the Earth orbits the sun. What people forget is that the sun is orbiting something too. Our entire solar system is flying around the center of the Milky Way at roughly 500,000 miles an hour, taking something like 230 million years to go around once. The last time the sun was in this exact spot in the galaxy, dinosaurs hadn't shown up yet. Now, you might think one orbit is much like another. It isn't. And the sun's orbit, it turns out, is strangely, almost suspiciously, gentle. Here's what makes it gentle. The Milky Way is a spiral galaxy, with great glowing arms wound around its center. And those arms are dangerous places. They're where gas piles up and new stars ignite, where the biggest stars live fast and die in supernova, where the radiation and the gravitational chaos could wreck a fragile little planet that's trying to grow life. You do not want to spend a lot of time inside a spiral arm. The catch is that the spiral arms aren't fixed. They rotate too, like a pattern turning in the galaxy. And most stars move at a different speed than the arms do, which means most stars are constantly plowing into one arm, crossing through all that danger, coming out the other side, and then catching up to the next one. Over and over, for billions of years. But there's one special distance from the galactic center. It's called the co-rotation radius, where stars move at almost exactly the same speed as the spiral pattern itself. Sit at that radius, and the arms don't sweep over you. You drift along with them, keeping pace, rarely diving into the dangerous zones. It's the calm lane on the cosmic highway. Guess where the sun is? We sit remarkably close to that co-rotation radius, and on top of that, our orbit is unusually circular. Most stars, the same age as the sun, trace out more stretched, more elliptical paths that swing them in and out through the crowded inner galaxy and across the arms. The sun glides along a nearly perfect circle, threading the gap, keeping its distance from the worst neighborhoods. So out of all the orbits the sun could have ended up on, it landed on one of the few that minimizes how often we get exposed to the galaxy's most violent events. The one quiet lane. The one path where a planet might have a few uninterrupted billion years to turn pond scum into poets. Now, I want to be honest, because that's the deal on this channel. Some astronomers think this is genuinely special, part of what they call the Galactic Habitable Zone, a ring around the galaxy where conditions are calm enough for life to get a foothold. Others push back. Recent work shows that stars wander over their lifetimes, migrating inward and outward, which muddies the idea that any orbit is permanently safe. The sun might have started somewhere else entirely and drifted here. The debate is very much alive. But strip all that away, and you're still left with a quiet fact. We are, right now, sitting in one of the safest seats in the galaxy. Whether by luck, by selection, or by some migration we don't fully understand, our star found the slow lane and stayed in it long enough for us to wake up and notice. And somewhere out there, most stars are still crossing the arms, taking the hits, while we coast along in the quiet. Number 6. The unchanging number. There's a number hiding inside every atom in your body. It's the ratio between the mass of a proton and the mass of an electron, and it comes out to about 1,836. A proton is roughly 1,836 times heavier than an electron. That number is everywhere. It helps decide how atoms hold together, how chemistry works, how molecules form, which means it helps decide whether you can exist at all. It is woven into the fabric of matter, and nobody can tell you why it has the value it does. It just does. 1,836. But that's not the strange part. Here's the strange part. A few years ago, a team of astronomers decided to check whether that number has always been 1,836. Because some theories, serious ones, attempts to go beyond our current physics, predict that the so-called constants of nature might not be truly constant. They might drift, very slowly, over the lifetime of the universe. And if you could catch them drifting, even by a hair, it would crack physics wide open. So how do you measure a number from the deep past? You look far away, because looking far into space is the same thing as looking back in time. The light reaching us from distant objects left them billions of years ago. The astronomers pointed the Very Large Telescope in Chile at a quasar, a blazingly bright object powered by a giant black hole, almost unimaginably far away. And in front of that quasar, between it and us, sat a cloud of gas containing molecular hydrogen. As the quasar's light passed through that cloud, the molecules absorbed certain very specific colors, leaving a kind of barcode printed in the light. And the exact spacing of those lines depends on, you guessed it, the ratio between the mass of the proton and the electron. The light they were reading had been traveling for 12.4 billion years. They were measuring that number as it was when the universe was barely more than a tenth of its current age. The result? Identical. The proton-to-electron mass ratio, 12.4 billion years ago, was the same as it is today, to within about 1 part in a million. No drift, no change. Across almost the entire history of the universe, that one number sat, frozen, unmoving, refusing to budge. And I know, a constant stayed constant doesn't sound like a headline, but flip it around. We have theories suggesting these numbers should shift over cosmic time. We have a universe that has changed in almost every other way. Galaxies forming, stars being born, and dying. Space itself stretching out enormously. Everything moved. Everything evolved. And in the middle of all that change, this number, and others like it, stayed nailed in place with a precision that's frankly hard to believe. Why? Why should the universe permit a number this important to stay so perfectly still for so long? What is holding it there? We don't know. We don't have a theory that explains why the constants take the exact values they do, let alone why they refuse to wander. So there it is. A number you carry around in every atom, set to a value nobody can explain, and held there, motionless, across 12 billion years of cosmic chaos. The universe rewrote almost everything. It left that one number exactly where it found it. Number 5, the horizon problem. I want you to imagine two people who have never met. They've never spoken, never exchanged a letter, never been in the same room, never had any way to contact each other across their entire lives. And yet, when you ask them to pick a number between 1 and 1,000,000, they both say the same number. Not close, exactly the same. To 6 decimal places. You would not believe it was chance. You would assume they'd somehow communicated? There's no other sane explanation. Now, make those two people two opposite edges of the universe. That's the horizon problem, and it's one of the deepest puzzles in cosmology. Everywhere we look in space, we see a faint glow left over from the Big Bang. It's called the cosmic microwave background, and it's the oldest light there is. Radiation released about 380,000 years after the universe began, when it had cooled just enough to become transparent. It fills the entire sky. And we can measure its temperature. That temperature is about 2.7 degrees above absolute zero. Cold. Faint. And here's the remarkable thing. It is almost perfectly the same in every single direction. You look at one side of the sky, you measure the temperature. You look at the exact opposite side, you measure again. And the two match to about 1 part in 100,000. The whole sky is the same temperature. Smooth, even, uniform, everywhere. Why is that a problem? Because of how things reach the same temperature. If you put a hot cup of coffee in a cold room, eventually they even out. The heat flows. Things mix. Everybody settles to the same temperature. But that takes time, and it requires contact. The coffee and the room have to be able to influence each other. Now think about those two opposite sides of the sky. For them to have settled to the same temperature, they would have had to be in contact at some point. Close enough to exchange heat and even out. But when you run the standard Big Bang clock backward, you find they never were. They were always too far apart. Light itself, the fastest thing there is, would not have had enough time in the whole history of the universe up to that moment to travel from one side to the other. They have never, ever been in causal contact. They could not have swapped a single particle of heat. And yet, they're the same temperature. To 4 decimal places. 2 regions of the universe that, by every account we have, never touched, never communicated, never had any way to coordinate. And they came out matching. It's the cosmic version of those 2 strangers picking the same number. Either it's the most outrageous coincidence imaginable, the entire universe just happening to start at the exact same temperature everywhere, for no reason, or something we don't fully understand allowed those regions to talk when they shouldn't have been able to. The leading idea is called inflation. The proposal is that in the first unimaginably tiny fraction of a second, the universe was a single, microscopic patch, small enough that everything was in contact and could even out. And then it suddenly, violently ballooned, stretching that one uniform patch into the whole sky we see. So the regions match because they were once neighbors, before space blew up between them. It's elegant. A lot of cosmologists are convinced. But inflation brings its own questions, and we've never directly observed the thing that supposedly caused it. So we're left looking at a sky that agreed with itself across distances it should never have been able to cross. The whole universe, somehow, on the same page. And we're still not entirely sure how it got there. Number 4. The flatness problem. The universe has a shape, not the stuff in it, space itself. Its geometry. And it can come in 3 flavors. It could be closed, curved in on itself like the surface of a ball, where if you traveled far enough in a straight line, you'd come back to where you started, and where gravity would eventually win and pull everything back into a crunch. It could be open, curved the other way, like a saddle, doomed to fly apart forever, faster and faster. Or it could be flat, perfectly balanced right on the knife edge between those two, the geometry you learned in school, where parallel lines stay parallel forever. We've measured it, and as far as we can tell, the universe is flat. Almost perfectly, exactly flat. That sounds reassuring. Tidy, even. It is, in fact, terrifying. Because flat is the hardest possible thing for a universe to be. Here's the problem. Whether the universe is closed, open, or flat depends on its density. How much matter and energy is packed into each chunk of space, compared to a very specific critical value. If the density is even a hair above critical, space curves closed and eventually collapses. A hair below, and it curves open and flies apart. Land exactly on critical, and you get flat. And this balance is unstable. Wildly unstable. It's like trying to balance a pencil perfectly on its sharpened tip. The tiniest lean in either direction, and gravity takes over and it falls. And it falls faster the longer it goes. In an expanding universe, any tiny deviation from perfect flatness in the early days gets amplified enormously as time goes on. A small imbalance at the beginning becomes a gigantic one later. So for the universe to look flat today, after 13.8 billion years of that amplification, it had to start out almost incomprehensibly close to perfectly flat. How close? When physicists run the numbers back to the earliest instant we can sensibly talk about, the density had to match the critical density to within about 1 part in 10 to the 60th power. Let me try to make that number real, even though it's basically impossible. 1 part in 10 to the 60th. That's a 1 followed by 60 zeros. It's a level of precision so absurd that comparisons start to break down. Imagine balancing the entire mass of the observable universe and getting it level to within the weight of a single atom. And even that doesn't really do it justice. If, in that first instant, the density had been off by 1 part in that ungodly number, too much by the faintest imaginable sliver, the universe would have recollapsed into a crunch long before any galaxy, any star, any planet, any you could form. Off by that sliver the other way, and everything would have flown apart so fast that nothing could ever clump together. No structure. No us. Instead, it landed on the knife edge, and it stayed there. Now, again, the leading explanation is inflation. That early burst of expansion would have stretched space so dramatically that any curvature got flattened out, the way blowing up a balloon to the size of the Earth would make any patch of its surface look flat to an ant. So inflation, if it happened, drives the universe toward flatness naturally. But notice what we've done. To explain one piece of impossible fine-tuning, we've leaned on a mechanism that needs its own carefully tuned starting conditions to work. We may have just moved the coincidence somewhere harder to see. The pencil is still standing on its tip. We've just told a story about who might have balanced it, and whichever way you turn it, the fact remains. Everything you have ever known or loved or seen exists because the early universe walked a tightrope 1 part in 10 to the 60th wide and didn't fall. Number 3, the Hoyle resonance. You are made of carbon. The chair you're sitting in, probably carbon. Every living thing on Earth is built on a backbone of carbon atoms because carbon has this magical ability to link up into the long, complicated chains that life requires. Carbon is the element that makes biology possible. No carbon, no you, no anything like you. So here's the obvious question nobody asked for a long time. Where does carbon come from? It's not made in the Big Bang. The Big Bang gave us mostly hydrogen and helium, the 2 simplest elements, and almost nothing heavier. Everything else, the carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was forged later, inside stars. Stars are the factories that build the heavier elements and then scatter them across space when they die. But carbon is a problem to build. To make it, a star has to slam 3 helium nuclei together to form 1 carbon nucleus. The trouble is, getting 3 things to collide at the same instant is incredibly unlikely. 2 helium nuclei can fuse, but what they make is desperately unstable. It falls apart in a tiny fraction of a second, almost always before a third one can arrive. The window is impossibly narrow. By rights, stars should barely be able to make carbon at all, and yet the universe is full of it. In 1953, a brilliant, stubborn astronomer named Fred Hoyle looked at this and made a leap that still gives physicists chills. He reasoned backward. Carbon exists, he said. We're made of it, so obviously stars can make it. Therefore, there must be something that makes the reaction work. some special property of the carbon nucleus that we haven't discovered yet. Specifically, he predicted that the carbon nucleus must have a particular energy level, a resonance, sitting at a very precise energy, around 7.65 million electron volts, a kind of perfectly tuned rung on a ladder that lets the reaction slip through that narrow window and actually happen. Nobody had ever seen this energy level. There was no evidence for it. Hoyle predicted it purely because, without it, he couldn't exist to do the predicting. And then they went and looked. Willie Fowler's laboratory tested Hoyle's wild claim, and they found it. A resonance in the carbon nucleus, sitting at about 7.65 million electron volts, within a whisper of exactly where Hoyle said it would be. He had predicted an unknown property of the universe, sight unseen, on the grounds that life requires it, and the universe complied. Now here's the part that keeps people up at night. That energy level isn't just conveniently placed. It's finely placed. The calculations suggest that if that resonance were shifted, even by a few percent, stars would produce drastically less carbon, or essentially none at all. Nudge the dial a little, and the universe becomes a place where carbon is rare, and complex chemistry and life never get their chance. The setting that allows you to exist sits inside a narrow window, and the dial is parked right in the middle of it. Why? Why is that nuclear energy level tuned to the one value that fills the cosmos with the element life needs? We do not have an answer. There's no deeper law we know of that forces it to be there. It simply is. Sitting in exactly the right place, as if the universe knew, somehow, that carbon would matter. Fred Hoyle, who was not a religious man, found this so unsettling that he famously said it looked like the universe was a put-up job, as though a super intellect had monkeyed with the physics. He didn't mean it as theology. He meant it as a confession of how strange the coincidence really is. And it's still strange. The furnace inside every star is set precisely to make the stuff that you are made of, and nobody can tell you who said it. Number 2, matter and antimatter. This is the big one. This is the coincidence that everything else depends on, including the fact that there's an everything else at all. Here's something physics is very confident about. For every kind of particle in the universe, there's a mirror image twin called an antiparticle. The electron has the positron. The proton has the antiproton. They're identical in almost every way, except their charges are flipped. And there's one more thing about them you need to know. When a particle meets its antiparticle, they annihilate. They destroy each other completely, vanishing in a flash of pure energy. Matter and antimatter cannot coexist. They erase each other on contact. Now, wind the clock back to the Big Bang. The early universe was a furnace of energy, and out of that energy, particles were being created constantly. But here's the rule. When you make particles out of pure energy, you make them in pairs. One particle, one antiparticle, every time. That's how the books are supposed to balance. Energy becomes a matter particle and an antimatter particle, together, always. So the early universe should have produced exactly equal amounts of matter and antimatter. And then, as everything cooled, all those matched pairs should have found each other and annihilated. Every particle meeting its twin, everything canceling out, the entire universe converting itself back into a sea of light and radiation, with no matter left over it all. No stars, no planets, no galaxies, no carbon, no chemistry, no life. Just an endless, expanding glow. That is the universe we should have. By the symmetry of the laws as we understand them, that's the universe the equations predict. But that's not what happened, because you're here. Somehow, in that great annihilation, the books didn't quite balance. For every 1 billion matter particles, there were only 999,999,999 antimatter particles. One extra particle of matter per billion, a tiny, almost invisible surplus. And when the dust settled, when all the matched pairs had annihilated and turned to light, that 1 in a billion surplus was all that survived. That leftover, that rounding error, that faint imbalance is everything. It's every galaxy. It's every star you've ever seen. It's the Earth. It's the atoms in your hand. We are, all of us, the tiny fraction that didn't get canceled out. The survivors of a near-total annihilation that should have been total. So what tipped the scale? What made matter win, even by that razor-thin margin? Physicists have a name for the imbalance. They call it baryon asymmetry, and they know roughly what conditions would be needed to produce it. Back in 1967, the physicist Andrei Sakharov laid out the 3 ingredients required. One of them is that nature has to treat matter and antimatter slightly differently, not equally, just a hair off. And here's the genuinely maddening part. We have found that asymmetry, nature does treat them differently. In fact, just in 2025, the giant LHCb experiment at CERN announced the first time they'd ever caught this imbalance happening in a class of particles called baryons, the same family the proton belongs to. It was a real, measured difference between how matter and antimatter behave. A milestone. But when you add it all up, every difference we've measured, every bit of asymmetry in our current theory, it falls short. Catastrophically short. By many, many orders of magnitude. The amount of imbalance built into the known laws of physics is nowhere near enough to explain why a whole universe full of matter survived. The numbers we can account for are a tiny trickle. The flood that actually happened needs something more. Some other source of asymmetry, some new physics we have not yet discovered, must have reached in at the very beginning and tipped the scale. We don't know what it was. We just know that, without it, there's nothing. No light to read this by, no eyes to read it with. The most important event in the history of existence, the moment matter beat antimatter, happened for a reason we cannot yet name. You exist because of a coincidence 1 part in a billion deep. And the universe has not told us why it broke in your favor. Number 1. Dirac's large numbers. We've spent this whole list looking at single strange coincidences. 1 number frozen in time. 1 nuclear level set just right. 1 imbalance that let matter survive. But what if the coincidences themselves were connected? What if they were all whispers of the same hidden thing? That's the thought that haunted one of the greatest physicists who ever lived. Paul Dirac was a giant. He helped invent quantum mechanics, predicted antimatter before anyone had seen it, won the Nobel Prize. He was famously, almost painfully precise. A man who did not say things lightly. And in 1937, Dirac noticed something about the universe that he could not let go of. He started comparing the fundamental numbers of nature, not the messy ones, but the deep ratios. Pure numbers that come out the same no matter what units you use. And he found something bizarre. Several of these enormous numbers, drawn from completely different corners of physics, kept landing in the same place. Take 2 particles, say a proton and an electron, and ask how strongly they pull on each other through electricity compared to how strongly they pull through gravity. Electricity wins, overwhelmingly. Gravity is staggeringly, almost comically weak by comparison. The ratio between the 2 forces is a number around 10 to the 40th power, a 1 with 40 zeros after it. An absurd, towering number. Okay, now ask a completely different question about the universe as a whole. Take the age of the universe and measure it not in years, but in the most natural tiny tick of atomic time. How long light takes to cross a single fundamental particle. How many of those atomic ticks fit into the whole history of the cosmos? The answer is also about 10 to the 40th power, or near enough to make you stop breathing for a second. Two questions that have nothing to do with each other. One about the relative strength of forces between two specks. One about the entire age of the universe. And they give you the same impossible number. 10 to the 40th. And there were more. Dirac kept finding these giant quantities from unrelated areas of physics, all clustering around the same scale, or simple powers of it. The deeper he looked, the more the universe seemed to be repeating one number back to him. Now, a lesser thinker might shrug. Big numbers are big. Maybe they collide by chance. But Dirac refused. He found it impossible to believe that quantities this enormous would match by accident. The odds to him were absurd. He became convinced that the matching meant something, that there had to be a deep, hidden connection between the physics of the very small and the structure of the whole cosmos, that these numbers were equal for a reason. And then he took the leap that still echoes today. He pointed out that one of those numbers, the age of the universe, obviously changes. The universe gets older. So if these giant numbers are genuinely locked together, always equal, then the others have to change too, to keep up. Which means the so-called constants of nature, things like the strength of gravity, might not be constant at all. They might be slowly drifting over the lifetime of the universe, in lockstep, to keep that great coincidence true. Dirac suggested gravity itself might be very gradually getting weaker as the cosmos ages. Think about what that means. It means the laws of physics might not be fixed scenery. They might be quietly moving, evolving, changing as time goes on, so slowly that across a human life you'd never catch it, but across billions of years, real and steady. So physicists went looking. They tested whether gravity is weakening. They searched for the drift Dirac predicted, and mostly, they haven't found it. The changes his idea required don't seem to show up in the measurements. So in its original form, Dirac's hypothesis is on very shaky ground. But here's why this is the number one spot. Knocking down Dirac's explanation does not make the coincidence go away. The giant numbers still match. The strength ratio of the forces and the age of the universe in atomic ticks still land on the same impossible value, right now, in our era. Dirac offered an answer, and the answer looks wrong, but the question is still standing there, exactly as strange as the day he asked it. There's a famous counter-argument from a physicist named Robert Dicke that's worth sitting with. Dicke said, maybe it's not a coincidence and not a deep law. Maybe it's about us. Creatures like us, made of carbon, can only exist during a specific era in the universe's life, after the first stars have lived and died and seeded space with heavy elements, but before all the stars have burned out. And it just happens that during that life-friendly window, those big numbers line up. So we're not seeing a miracle. We're seeing the only time we could possibly be around to look. Which is clever. And maybe it's right. But notice what it's really saying. It's saying the only reason the universe looks fine-tuned to us is that, in a universe where it wasn't, we wouldn't be here to be puzzled by it. That's not exactly comforting. It just trades one mystery for a deeper one about why there's anyone here at all. And that's where we land, at the end of all of it. 10 coincidences. A dark sky that turned out to be a clock. A number frozen across all of time. A universe balanced on a tightrope 60 zeros wide. A furnace tuned to make us. A scale that tipped just far enough to let matter exist. And underneath them all, the suspicion that gnawed at Dirac. That these aren't separate accidents at all, but glimpses of some single pattern we can see the shape of, but cannot read. We are very good at measuring this universe. We can weigh a proton against an electron. We can read a number off a quasar 12 billion light-years away. We can balance the geometry of all of space to one part in a number we can barely write down. But measuring is not the same as understanding. And every one of these coincidences is the universe handing us a number that's exactly, impossibly right, and refusing to tell us why. Maybe it's chance. Maybe it's selection. Maybe it's a law so deep we haven't even learned how to ask about it yet. But every time we look closely at the fine print of reality, we find the same unsettling thing. It fits together a little too well, as if someone, or something, or some principle we don't have a name for, set the dials, and then walked away before we woke up to ask any questions. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next